are, so it just produces the whole output in one go instead of word by word.
Interesting.
They're just so weird.
Alright. So, wait, let me just make sure this is.
You're not in a.
Am I not?
You're like on the edge.
Right.
Can you make this lecture related to diffusion models? Thanks.
Of course. Anything for you, Gordon.
Got it.
Okay. So I didn't really prep for this lecture, so I'm just gonna be rambling for a lot of it. But
It's recording.
yeah, is it good?
Yeah, it's
Okay.
recording. Yeah.
Yeah, I have 2 textbooks on my computer over there in case I need to search things up. The topic of today's class is gonna be connections, curvature, and vector bundles. But before getting to that, I'm gonna give some final remarks on Hodge theory. So I hope you guys found it interesting because I think it's a really nice way to prove things and it gets you quite far. In topology, because there's a lot of things like, for example, in complex geometry, where you can say, okay, let's pick a Hodge class under these conditions, and then do some local computation to show that the Hodge class has to be 0, and then somehow give some consequence about some cohomology statement, which is a pretty powerful thing to do. So it allows you to do like analysis on topology. So I'm gonna make 3 remarks. The first one I'm gonna say now, the third one I'm gonna say after we talk about connections and curvature. So first off, a little bit about Lee groups again. So 2 weeks ago we did cohomology of Lie groups, and we found that left invariant forms are in one-to-one correspondence with the exterior algebra of the dual, the Lie algebra. And so this allows us to compute the cohomology of a Lie group once we figure out what the differential is, strictly in terms of the Lie algebra, and then you can just reduce the computational cohomology, remove all the calculus from it, and just do linear algebra. So you can have, these are like pretty symmetric forms, but you can have even more symmetric forms. So if you have a compact manifold, I guess this also leaves compact, but then you can consider bi-invariant forms. And so what this means is left and right invariant. So it's invariant in left and right group actions. And so these are like much more symmetric than this guy. And so if you read the paper by Chevalier on cohomology of Lie groups and Lie algebras, he shows that if you have a bi-invariant form, then you can have a condition on that based on the commutator. And based on the explicit formula that we found for the exterior derivative in this side, you immediately have that if you have a bi-invariant form, it's closed. And in fact, it's also true that every cohomology class has one and only one bi-invariant form. So it looks like Hodge classes and it smells like Hodge classes, then it must be Hodge classes. So it turns out that bi-invariant forms are Hodge classes on Lie groups. So that's a nice sort of class of like, quote unquote explicit examples that you can construct. And I guess when I say Hodge classes, the Hodge classes depend on the metric that you choose, again, because you're using the Hodge star and whatnot. So with respect to what metric, well, you're gonna want a bi-invariant metric. On a simple Lie group, there is, well, a simple Lie group is like something which can't be broken down any further, and there is one and only one. You can reduce this to a Schur's lemma type statement, where a map between irreducible representations has to be some multiple data entity. And for semi-simple groups, I'm sure that there's something similar that you can do. Okay, so that's Lie groups. Second comment is ENI. So you can go up to your physics friends and tell them that they spent a semester learning about electromagnetism, and then you can state the free field, like the free space Maxwell equations, which means no charges or currents, in like a single sentence, which is that the electromagnetic tensor is harmonic. So you have this object that shows up, which looks like zeros on the diagonals, and then you have the electric fields over here and the magnetic fields on this smaller square. And it turns out that Maxwell's equations are equivalent to the two equations that df is equal to 0 and d star f is equal to 0. What do I mean by this? So the electric field and magnetic field usually you see as vectors, but really the electric field should be thought of as a one form. I think I discussed a little bit earlier about how forces can be thought of as one form, so the electric field is a force, and the magnetic field should be thought of as a two form. In my opinion, if you actually formulate electromagnetism in this way, a lot of forms become clearer, and you can kind of see that if you extend this beyond 4 dimensions, then you have a lot more B field terms than E field terms, and that's because you have a lot more two form things than one form things. And so F itself is also a two form. So this row is like 1, 4 wedge AP, and this one looks like the spatial two forms. So then this fact that df is equal to 0 comes from some general statements, because you can interpret electromagnetism as sort of being some curvature of a connection, which we'll discuss in a bit. And then this guy follows from, if you look at the Lagrangian way of doing electromagnetism, it turns out the Lagrangian for the electromagnetic field is just this quantity, which we said that if you minimize this quality, it's equivalent to solving these two equations. And how does this get modified if you have an inhomogeneous space? So if you have charges and currents, this gets replaced by J, where J is the forecurrent. So this looks like charge and the usual 3 current vector. And I guess one other thing to say about this is you can consider a one form, which is A, which is the electromagnetic potential, and this looks like a 4 vector phi, the vector for potentials. This is the electric potential, and this is the vector magnetic potential. And then you have the equation that F is equal to dA. So this is essentially saying that A is the potential of F. And then this condition immediately applies this because d squared is 0. And then this comes from minimizing this. So you can see that like somehow electromagnetism has a lot of differential forms and cohomology embedded into it. Okay, so now let's move past Hodge theory and start talking about vector bundles, connections, and curvature. So, I guess starting talking about vector bundles. So, one quick definition is a vector bundle is a map of space. Okay, so a vector bundle of rank K over some space B is space B, such that, and a map B from A to B, such that P inverse, or I guess we call this pi. This is some projection. Pi inverse of any point P is going to be homeomorphic to R to the K. So that's where the rank part comes from. So what's the picture for this? You have some sort of a base B, and above this, you have to every point a vector space. And these things can kind of twist around and do some funny things. And so there's a condition on this that, okay, I don't know if I want to say the condition formally, but the idea is like these sort of vector spaces have to vary continuously. And I guess one way to sort of see what happens is like, sort of you want this point on this vector space to be close to a similar point on a nearby vector space. So what I like to imagine is like if you have a file cabinet, right, you have a bunch of like folders and stuff which are right next to each other. So So they all look like planes, but they're sort of like disconnected from one another. On the other hand, this is like more of like a solid cube, which you can split up into planes, but you can move from one plane to another plane, sort of in a continuous fashion. Yeah.
Is pi here just a continuous map, or is it like diffeomorphism?
Oh, it's definitely a diffeomorphism. We will be considering smooth maps. So you can pick like local charts on E, and then the map is like differentiable.
Okay.
I mean, yeah, just assume everything here is differentiable because we need to use derivatives in order to do ground cohomology or any sort of differential forms at all. Okay, so this is the definition of a vector bundle. So then some examples are tangent bundles. So if you have any manifold M, then you can consider Pn, which at the point x has the vector space of the tangent space to x. And the tangent space is, you know, like, what are the different directions that I can move in my manifold? Maybe I can mention something interesting, which is the tautological bundle. Of Pn. So, or I guess this is Cpn. So Cpn, we've discussed is the space of lines in Cn plus 1 minus 0. So if you call this space E, then you can have a projection of E down onto Cpn, and above every point you have a copy of C. And sort of the schematic picture is like, if you have like R2, for example, then this is like a picture of RPN, remember, where you have to identify opposite points. And above this point, you have this copy of C. Or I guess this shouldn't be E, but this should be like, E minus zeros. So away from 0, I mean you have a unique point. Every line corresponds to a unique point on CPN, but then the 0 point is shared amongst all things. So you have a different copy of 0 for each fiber. So what it's saying is for every point, associate the line in Cn plus 1, which this point represents. Okay, and another example that we've seen is normal bundles. And over here, you have some big manifold M. Inside you have some smaller manifold N. And then if you sort of look like very closely to it, then you can look at the normal directions and you get the normal bundle to your submanifold. And we sort of saw that there's like some non-trivial things about these. And the way that we saw that was, if you take sections of these guys, then a section of this bundle corresponds to a vector field. A section of this bundle sort of corresponds to an infinitesimal deformation. Section of this bundle is like some, I guess you can probably get some interpretation of that. And so we saw something like there are cases where sections of the bundle must have a 0 locus. So you can't have a non-vanishing section. And so that sort of shows you that these things are a bit richer than just taking B cross R. So if you have a rank K vector bundle, that does not necessarily mean that it's just the product R to K. What this means is like you sort of have some sort of twisting going on. So one way I like to I was confused about like what this looks like for a bit. So one picture which I really like is like on the sphere you consider the tangent bundle, which is like a lot of these different planes. And So these planes are sort of like rotating around, right? And I was like thinking of this kind of like, I think like chainmail, like a bunch of like different things tied together that you can like sort of bend and move and stuff. So if you try and trivialize this into the sphere cross R2, then one way to do that would be like this top one is flat, but for example on the equator the things are vertical. So if you can like sort of fold each one of these so that they become horizontal, then that would be an identification of the tangent bundle with the sphere cross R2. But if you try and visualize that, like you'll realize that as you flatten things out, things will get more and more bunched up at the bottom. And so you can't flatten things out on the entire thing. So vector bundles are sort of this interesting object where locally you have a trivial thing, but globally you can have some funny pieces going on. Yes?
What does this total space look like?
Well, it's a 4-dimensional space, so it's a bit hard to visualize. Sort of like when we were talking about, so there's two ways I guess you think about it. One is like if you don't care about immersed manifolds, then you can just like attach a plane to every point on S2 and just have the planes overlap each other, and it's like that's fine. And then that's like what your manifold looks like. But the way that I like to think of it is like with differential forms, right? We had like each different point was a different copy of a differential form. So over here it's kind of like at each different point we have a copy of r to the k. And so this is like a parameterized families of r to the k, where the parameter space is our base manifold. Makes sense? Okay, so yeah, and I guess there's like a motif, which is study vector bundles via sections. And what's a section? A section is a map. So over here we have a projection map in the tangent space M, right? A section, so this is pi. A section is a map going the other way, so that the image of every point lies in the fiber that it has. So it's essentially it's a vector field where the vectors are vectors inside this vector bundle that you have. And as we've seen, if you have some sort, you can have some non-triviality where any section must vanish. And sort of, I guess, a converse statement to that is if there exist sections S1 through SK on rank K vector bundle E, then such that for every point on the base, S1 at P, SK at P, where these are all vectors lying inside the fiber at P, so this would be inside E sub P, are linearly, or sorry, form a basis. Then that implies that E is isomorphic to B cross R to K. And what's the idea for this? It's essentially that each, at every point, these K sections give you a basis at that point. So finding K non-vanishing sections which are all linearly independent is equivalent to saying that your vector bundle is trivial. So non-triviality is almost tautologically like some vanishings of vector bundles, of sections of the vector bundle. And so something really interesting that we'll see from this is that one way that you can measure this failure is via something called curvature. And curvature sort of tells you like how much your vector bundle is sort of rotating around, right? So we said that this one can't be flattened all the way. This one sort of has like uniform curvature because like you can see the planes are sort of moving around in a uniform way. If you try to flatten out the curvature a lot, then things get bunched up a lot near the bottom. So it'll have zero curvature over here because all the planes are sort of parallel to each other, but then near the bottom it'll have a lot of curvature. So it turns out that the total amount of curvature you have on your manifold, in a sense, is constant. And one way to formulate that is that you get these homologic classes coming from the curvature of your vector bundle, and that can be used to detect non-triviality of your vector bundle. And these homologic classes, they're called Chern classes. They also have a lot of nice properties. They are very computable in some cases, and they give you sometimes examples of connections where you can't really hope to, some examples of differential forms where you can't really hope to get nice differential forms through like an explicit hands-on way of doing things. Cool. Any questions so far on what vector bundles look like? Do they feel motivated, or does it feel like I'm just throwing something random out there? I'll take a shrug. That's better than a no.
No, there's one better.
Okay, so the first thing we're gonna do is we're gonna put some rigidity on these vector bundles. So what do I mean by that? I guess topology is often said like it's the study of spaces where you can like deform things a lot. So like for example, like the sphere is the same thing as the sphere with like I guess a little indent down here. So you sort of deform things. And similarly with vector bundles, like I said, you can kind of like move around the planes and stuff. And so what connections do is they sort of rigidify what you're talking about. And they allow you to compare vector spaces, nearby vector spaces, I guess. So I guess I'll give a couple definitions as to what a connection is as we go along. But the idea of a connection is to identify nearby vector spaces. Okay, so why might one want to do this? So there's two interesting places where this comes up, I guess. One is that if you are talking about Riemannian geometry, we kind of discussed this a little bit earlier, but if you put a metric on your space, to remind you, a metric tells you what unit length vectors look like, and if they sort of get stretched out like this in your presentation, then what that means is that your manifold sort of doesn't actually look like this. What you'll have to do is like shrink these vectors down. So what it might end up looking like is something more like this. So if you put a metric on your space, which tells you how long vectors are, then that influences what the shape of your space is. And the idea of a tangent bundle is that a tangent bundle kind of is the same as local information of vector space. So this can be understood by sort of understanding something called the Levi-Civita connection on the tangent bundle, which hopefully we'll get to talk about at some point. But the idea here is that you want to say that, okay, these two vectors don't quote unquote look the same, right? But then if we sort of fold it up, then this guy shrinks, and so these now quote unquote look the same. But this is sort of like just the way that I've drawn it. So it kind of depends on like how you draw the thing, right? So how can we say whether or not something looks the same regardless of how we draw it? So what we need to do is we need a way to compare this vector space over here to this vector space down here in order to say whether these vectors look the same as these vectors, right? So that's reason one why you might want a connection. Reason two is in physics, you have a lot of derivatives. So for example, what happens is like you have like an electromagnetic field, and then you have a lot of these equations which compute like derivatives of electromagnetic fields in different settings. And so you might think, okay, so if I have an electromagnetic field, I mean, like it's pretty easy to differentiate normally, right? But then if you're a mathematician, you can ask 5 things like, what if I want to do electromagnetism on a 4-dimensional sphere? Which, I don't know, some physicists care about, but I guess your average freshman physicist wouldn't care that much. But if you want to generalize such a theory, such a quote-unquote field theory, where at every point you associate a vector to like sort of in a mathematical framework into manifolds, then like this is sort of forced upon you that if at every point you associate a vector, and you need to differentiate to get from this vector, you need to differentiate to see how these 2 vectors change. Well, these 2 vectors live on completely different vector spaces. So if you want to define a derivative, then you need to compare vector spaces. Does this make sense? Ample motivation. Okay, so how can we compare vector spaces? Well, what you can do is you can find something called parallel transport. And so what's parallel transport? It says, here's your manifold, and you have some vector bundle E on it, which means at every point we associate a vector space. And say you want to compare this vector space to this vector space. So what you can do is you can say, okay, I'm gonna move along the base manifold to get from this point to this point. So you go from P to Q along the path gamma, where gamma is a map from an interval to your base manifold P. And then what parallel transport does is it associates to gamma some map P gamma. This is such that gamma naught is equal to P and gamma 1 equals Q. So this is just a path from P to Q. And to every such path, it's gonna associate a linear map from P sub P, so the fiber at P, the vector space at P, to P sub Q. And the idea of this is like basically as you move along gamma from P to Q, you're like rotating the vector field that follows along how it changes until you get to your endpoint Q. So the reason this is a lot of data is because this plus, so this is parallel transport plus conditions. I don't remember what the conditions are, but the idea is that for every path, you sort of follow along how this thing twists and turns until you get to your endpoint. So if you choose a different path, what can happen is like, it can twist and turn in different ways, and then when you get to your point Q, you end up with a different linear transformation. So P of gamma does not have to be independent of gamma. It very often does depend on what path you choose to go between the different points. Yeah.
For a given manifold, and like I guess a given set of paths, is the parallel transport uniquely defined, or can you choose multiple different ones?
You can choose many different ones, right? So it's like a lot of data. Like how do you? So I guess like I gave the picture of like twisting and turning, but like in general, like you don't even you can just like arbitrarily prescribe these things. But you want it to be sort of nice in the sense that like if you start over here and you move to a very close nearby point, you don't want it to be like a reflection by 180, right? So the idea is you can build up parallel transport by sort of breaking this down into a bunch of different segments. And then you look at parallel transport from this segment, this segment, this segment, this segment, this segment. And then the goal is to try and define things in such a way so that if you have 2 points that are nearby, then these identifications are going to be very similar to them. And so that way, sort of, I guess if gamma is quote short, this is just like an idea, then P is approximately big N math. So, like I said, one of the reasons that we want a connection is to be able to take derivatives of things. So one way that we can describe this is we can sort of take, this feels like a derivative, right? You try to break up a big thing into a bunch of small little pieces. So we can try and see, okay, so what is the, if I call this interval T, what is like dp dt? So what does this mean? This should be like a linear transformation, which is like P is roughly the identity plus the derivative with respect to T times T plus something to higher order, right? So how should, so what should dp dt be? Well, dp dt is going to be like another matrix, right? Because this guy's a matrix, this guy's a matrix, so this thing's also going to be a matrix. So we can look at how dp dt acts on some vector. So we can look at this guy. And what is this saying? This is saying that if I guess I should also put the gamma on. So this is saying that if I move just a little bit along gamma, how does my v change? And so this is going to be the limit as t goes to 0. So what you'd like it to be is p, I also say p sub t for parallel transport from 0 to t. So p sub t of, or you'd like it to be like, I guess v sub t minus v over t. Okay. What the, let me draw a picture. So you have your starting point P here, and then you have your very nearby point Q, and above each of these you have a vector space, and above each of these, so you start over here, and then you sort of parallel transport your way along, and you're trying to see how your vector ends up. So if this is v of 0, then this is sort of v of gamma of t, which is like how much does your vector field change after going a little bit along gamma, right? So and this should really be p of gamma of t of v minus v over t. But the way I've defined parallel transport is it goes from your source vector space to your final vector space. So it should actually be the inverse of this transformation. So what you're looking at is you take a vector at the end, sort of parallel transport it back, and then divide by time. But then, what are you parallel transporting exactly? So this is like, you should have a vector field already on there, because it doesn't make sense to define parallel transport if you don't have parallel transport yet, in terms of parallel transport. So if you have some vector field already here, then you can sort of measure how much does this vector field change if I identify each vector space by the parallel transport goes. So this should actually be a vector field at least near P. Okay, and so this will be some other vector inside EP, which sort of says if this is our initial vector v, then this will be partial p partial t. So this is going to sort of rotate a little bit in this direction. And if this is another vector w, then maybe this guy moves in this direction. So sort of what your parallel transport in this case is doing is sort of shrinking it this way. I mean, depending on, but it depends on like how the vector fields are defined away from the point as well, right? So what you might expect is that if you sort of look really, really close to it, then your vector field near your point is going to look like the vector itself near the point. And what you should have is that this only depends on the direction in which you are moving. Right? So if you move, so this is your base point P, and if you move along, so this is your vector V inside VP, and if you move along this direction X inside PPM, you can ask how much does V change by? And so this finally is what is called a covariant derivative for a connection. So this is a function that looks like this. And so again, you need to like feed in two vector fields, right? So both V is a vector field in E, and X, technically it shouldn't depend on the things away from your point. But in order to define it, you also need this to be a vector field. But you can show that it actually only depends on the direction that you're moving at that point, so you can actually just make this into a vector. And so what properties does this satisfy? If f is a function, then you should have some sort of Leibniz rule. So what is this saying? This is saying that you have some function, and at every point, your vector field is a bunch of vectors at different points. And what you're doing is you're rescaling them at different points by different scale factors, which is determined by f. And so if you like sort of use this definition of parallel transport, then you can show that if you do this procedure of like differentiating with respect to parallel transport along some direction, then it will satisfy this sort of Leibniz rule, which is saying that this is how much f changes in the direction x times v, plus how much does v change in the direction x times f, right? And also you should have this case. Does anyone want to take a guess as to what this should be? Yeah.
Do you have like a chain rule type thing?
Right, so you might think that it should be some sort of chain rule or particle or something. It ends up being like much simpler. It's just f times the gradient of x v. And the reason for this is that what you're doing, you're scaling the direction that you're moving in, right? And so this is just saying if you move twice as fast in some direction, then the amount that your vector field changes should also be twice as fast. So a little definition here. Gamma of B is the space of smooth sections of E. And so what we have is that a covariant derivative is a map from gamma E to gamma E tensor omega 1. Okay, so what does this mean? Remember that omega 1m is something which eats in a vector and gives you a number. And this is basically at every point it gives you some vector in E. And so something in this space, remember that this is essentially take linear combinations of products of these two things. So it'll look like, if you look at like the gradient of some vector field V, and this will look like some linear combination of AV, which this is some linear transformation, times AIV times omega I, where this is some linear transformation on E at the point P, and this is some one form at the point P. And so what this means is that when you plug in a vector field X over here, each of these one forms is going to eat this vector, give you a number, and this is going to be a linear combination of them. So the AI is how much does this vector V change in each of the different directions. Does that make sense? Okay.
So this gradient's like a linear map, from the sections.
Yes. And, I mean, another way that you can write this is that the gradient is a map from gamma E cross gamma EM to gamma E. And this is saying, give me a vector field, give me some direction to move in, and I'll give you how much does the vector change.
Why can you do the direct product with just ends? Oh, why can't, I still, like, cause omega 1m takes in something in n and gives you a scalar.
Yeah.
Why can't you just treat that as like an input to the derivative? And then you do something.
Yeah, that's this guy. So you're treating the vector as an input to the derivative.
Oh, cause the tangent space.
The tangent space is the space of vectors.
I see.
The tangent, so this is saying either you can feed in the tangent space here, and then this sort of corresponds to this expression, or you can have something like this where you sort of like don't specify the direction that you're moving in yet, and it says, give me a direction to move in and I'll tell you how much it changes. So these are like two perspectives of saying the same thing.
Cause omega 1 takes in things from the tangent space, not
Yes.
from the manifold.
Yes. Any questions on that? Okay, so, I said that a connection is a way to relate nearby vector spaces. So you can sort of imagine that what happens is, as you go from this point to this point, in the direction x, I'll use capital letters for vector fields on the base, and something else for vector fields on E, or like capital X, Y, Z for vector fields on the base. So if you move in the direction x, you can ask, how much does this vector field change by? So it's like some sort of rotation or a scaling or something, right? So what this means is that another way to think of a connection is through a connection one form. And I'll tell you why I'm putting this in quotes in a second. So what this says is that give me a vector, and I'll tell you how much to transform my vector field by. So what that says is give me a vector, so you need an omega 1m, and you're going to tensor this with how much does your vector field change by, right? So so we know that this transformation has to be invertible, right? And so this goes back to the problem set 2 weeks ago. We have that the parallel transport should be an element of GLN, right? It tells you how much does this guy rotate or whatever. So what should sort of an infinitesimal transformation be an element of? Yeah.
Like the Lie group on that?
So the Lie group
Or like
is
the generator.
yeah. So the generator is the Lie group, which is the Lie algebra. So if you have the vector space, so this is rank K, then you have that if you move in some direction, it should be an element of the Lie algebra of your vector space. And your vector space is just locally R to the K, so this will be something like G, L, R. But this is the Lie algebra of transformations. Does this make sense, what I'm trying to say? It's essentially saying that to every vector that you input, so give me a vector, and what I'll give you is a vector field on my manifold. And this vector field on my manifold will tell you, if you move in the direction of the vector that you gave me, what is the little bit of transformation that my vector space is going to do, right? So, sometimes, I guess I'll make another definition here. Definition. Omega A of E is equal to omega K of M tensor E. So what this guy says is, give me K vectors, and I'll give you an element of E. And this sort of satisfies some sort of alternating property. So I think omega 1 of E is pretty well motivated. Give me a vector and I'll tell you something if you move in that direction. We'll have a need for omega 2E when we talk about curvature. Does that definition seem reasonable? I guess I'm suppressing the M on the left. But yeah, so, or I guess I should actually make M I E here. Okay, so you expect that you can describe a connection by having an element of this at every point. So globally what that'll look like is a connection is an element of omega 1 of, I guess I'll write it like this, G, L, E. So what's GLE? GLE is another vector bundle where at every point you have a k-square dimensional vector space. And that k-square dimensional vector space is the Lie algebra GLRK. So at each point you have like the k-dimensional vector space of sort of transformations that you could do on your vector space at that point. And this is saying, give me a vector, and I'll give you an infinitesimal transformation. And that's what a connection should do. But this is not quite right. And the reason it's not quite right is because if you're going to compare nearby vector spaces and say, I'm going to twist this one to get to this space like this, right? Then you're already claiming to have a predisposed identification of the two vector spaces. Because if you're saying that you're going to twist something to get to there, then that means that you already have to have an untwisted one to compare it to. So that means is that a connection itself is not an element of this guy, but if you have two different connections, two different ways to identify vector spaces, then it does make sense to say one differs from the other by a sort of rotation or a sort of infinitesimal transformation. So what this means is that if you have two different connections, which I'll denote nabla 1 and nabla 2, then if you take their difference, this is an element of this guy. Does that make sense? Does it make sense? Like, does this make sense beyond the level of symbols, what the idea is? Because if you just see the symbols, I don't think it really, I think it's pretty confusing. But if you understand the idea of like what each symbol means, then I think it makes sense. Yeah.
Is there a reason that you write as like a tensor product of the omega 1m instead of just like a mapping from gamma on the tangent space of m to the GLRK?
I sort of want to think of this as an object on its own. So I want to think of it as an object where give me a vector, or I guess you'll see later why it's useful to think of it as like this sort of object, but think of it as like, not like one vector at a time where like you give me a vector and tell you what direction to go in, but like a full object which is sort of like a function. And the function is give me some direction to move around it and I'll tell you how much you change by it. So that's sort of encapsulated by this guy tensor. This says give me some vector to move in and I'll tell you how much you change.
But for like every object like it, there is a corresponding linear map from gamma on the tangent space to the GLRK.
Yeah, that's exactly what this is.
Yeah.
Well, yeah.
Yeah.
Yeah, so this is exactly saying that at every point you have a map from the tangent space to GLK, which is prescribed. And so again, this is just saying that if you have two connections, then they differ by one of these. It's called, this is called an E-valued K form. So they differ by a GLE valued K form. Yeah. So let me discuss maybe a bit more explicitly how you can talk about these. So you can look in local coordinates. And so the condition on vector bundles that I did not write down is locally E restricted to some subset U, which this is some open subset of the base. This is homomorphic to U cross R to the K. And this is sort of what I was saying is that you have something on the base and you have like a bunch of copies of R to K which are sort of like stuck together and melded together in some way. But what this sort of says in our perspective is that locally you have something which is trivial. You can sort of see it if you don't rigidify anything using connection, which connection tells you how to identify nearby things. If you're allowed to move them around, you sort of move them around using this homomorphism so that all of them sort of line up in a straight line. And so what this means is that locally, there exists a trivial connection. And this connection essentially just identifies each fiber as being R to the K. And so that means is that if you locally section S restricted to U, yes, let me call this map phi. Phi 1 also. So phi 1 composed with S restricted to U is going to essentially just be a function from your base manifold to R to the K. And in this case, this trivial connection is going to look like this guy acting on this is just going to be the derivative with respect, or in the direction x, the derivative with respect to x of whatever this function is. So now, there's no reason that, or a priori it's not obvious maybe, and if you have a connection that this local trivialization is going to preserve the connection, in the sense that's going to make this connection exactly the one that lines up all these vector spaces, right? So I'll call this nabla trivial. So if we have, we already have a connection lambda nabla on E, which we want to understand, for example, then what does nabla look like on like in this local trivialization? So you have these guys lined up together in a line by this local trivialization. You want to understand what does our previous connection, which we sort of described a bit more abstractly as having some relationship between nearby vector spaces, look like after we take this transformation. And so we know that the difference of this nabla and this nabla trivial is going to be a one form, which takes values in the Lie algebra. So what this will look like is nabla will then be the derivative with respect to nabla in the direction of x, will then be the derivative with respect to x plus some sum of ai x to the I, where each of these is an element of GL R to the K. Right? So what this is saying is that if you differentiate with respect to this connection that you had on your abstract manifold, so maybe you have something where you have these vector spaces sort of rotating around in some way. And you trivialize it sort of by straightening these out. Then what's going to happen is that, like, in the process of straightening it out, you'll like have a different way of, or the way that you identify the vector spaces here will look different than the quote-unquote standard way of representing it here. And that difference is exactly represented by these connection one forms. So emphasis is that these are only defined after describing U and V1. So only after you choose a local trivialization does this work. So the point is that if you take a local trivialization, like you have your base manifold and you have like a bunch of vector spaces lined up, what you can do is like you can rotate these vector spaces in any which way that you want, right? So you come up with another local trivialization. So you can have phi 2 from E restricted to U, also isomorphic to U cross R to the K. And the way that you can do this is that phi 2 is equal to phi 1 composed with some, or I guess phi 2 at the point P, through phi 1 at the point P, times some element G, which is in the general linear group. So this is saying I'm going to choose some transformation of my vector space at every point, which varies continuously. And this gives me another trivialization of my vector bundle. So now, if you've twisted things more, then you should expect that these connection matrices are also going to change, right? So how do the connection matrices change by? I guess this is sort of language that physicists use almost exclusively to talk about connections and derivatives and stuff. But I think if you don't see it, then you get very lost in like talking about abstract connections and then never actually know how to compute anything with the connections, or like you get lost in the high level and don't actually know what's going on. So in this second localization, we have another trivial thing, which I'll call now the triv 2, and we have that our connection is equal to the first trivialization plus these matrices AI. And so I guess this is like one place where it already starts to show up that it's useful to think of nabla not as like explicitly giving you a vector at every point, but to think of it as sort of an object. So that way we can just write this vector of matrices instead of writing out each of these. So, or maybe I will write. Yeah, let's just write it. But this is equal to second trivialization of x prime plus the sum of ai x prime x I prime. So these are coordinates on your first space, and these are coordinates on your second space. And so what happens? Let's see here, how do I describe this? Yeah, so I said that you have a local trivialization here and a local trivialization here. So what this means is you are transforming some section S into some, in the local trivialization, into some new section G times S, where by G I mean at every point give me an element of the general linear group, which tells me how much should I change my trivialization by, right? So what you should expect is that G of this transformation of S should equal G, some sort of transformation of what my derivative looks like, which is to say, write the derivative in the second way, acting on this transformed section. Does that make sense? And so in order for this to be true, what you need is that G acting on this covariant derivative is equal to G nabla G inverse. What does this mean? This means first, so you've changed S into a new frame. So first change it back into your old frame. Or I guess maybe I should call this like nabla tilde or something. This is the same connection, but just expressed in new coordinates. So this nabla tilde is gonna say, first change g of s back into your old frame s, take the derivative that you had in your old frame s, and then change it back into your new frame. So it sort of acts by this transformation. And what that means is, so let's expand this out. So this is going to be delta in the first trivialization. So this will be g of partial x plus ai, g inverse. And remember that these aren't numbers, these are elements of GL R to the K. So what that means is that when you're multiplying this by group element, you're like multiplying the matrices together. And so what this becomes is so if we act on this on some section S, then the AI term is just going to be G AI G inverse acting on S. But then this term, you have to apply the product rule to this guy, right? So it becomes D partial G inverse times S plus G inverse partial S. So what this will be is G AI G inverse plus G partial G inverse S plus this is just G inverse, so those two cancel out, and then you get the derivative of S. And so what we see is that this is equal to these AI primes. So from the relation that nabla tilde is equal to the conjugation of nabla, you might expect that the matrices would also transform in that manner, but you actually get this other term, which corresponds to the fact that you're taking the derivative of something. So if you take like a physics class, then they'll say that this is like the transformation law for the Levi-Leader connection. Take a GR class. Or if you take like a QFT class, then this will be like the transformation law for a gauge field. And so this is essentially saying that these matrices are only defined locally, and if you go to another chart, they're going to be related like that. Okay, cool. So here is why this is a good thing. Because this whole conversation is a little bit complicated, like you're rotating things and then you want to do this. What if we can find a nice way of representing our connection? So what if we can rotate our planes in such a way such that the connection is flat, in the sense that the connection looks, this is also called a flat connection. So that the connection sort of just looks like taking the derivative of something, right? No coefficient matrices. If the transformation law for this, for the coefficient matrices was just this, then that would mean if it's 0 in one local trivialization, then no matter how you straighten out your planes, it'll be 0 in all of them. Which means that if it's non-zero to begin with, it would be non-zero to end with. But this makes things a bit more complicated. It adds a bit of hope in the sense that if you have something non-trivial, then maybe you can rotate things in a way so that this derivative of G term cancels out with the non-triviality of A, and you end up with something that's 0. However, this is also really hard to analyze, right? How are you supposed to sort of understand, how are you supposed to like combine these two terms in such a way that it perfectly cancels out and you get something trivial? And as I've already sort of hinted at, you can't always make things trivial. There are global obstructions. And sort of, again, with the picture of the sphere, what I want to say is like, you want to like flatten out all the planes, and then you realize that you're the one thing that bunched up a lot. And so maybe you can locally flatten things out, maybe you can't, but in some cases globally you definitely can. And actually, there are also local obstructions to deforming your thing into a flat connection. So I will start on this topic and continue it next time. Holonomy and curvature, i.e. non-triviality of connections. So this is a hard formula to work with. If we want to trivialize a connection, what we want to say is like, make a change of coordinates so that this guy's gonna be 0. Also, I will say, I mean, the first like 17 times that I saw this, I did not understand it. So I don't expect you to like understand this whole derivation now, but like I guess want you to see what it looks like so that you have some sense as to what things are. But our goal would be to like solve this equation for G with a fixed AI, because we have our connection fixed already, in order to make this 0, which is hard. So is there some other way that we can like sort of test for triviality of things? So one thing that we can do is we can say, if we do have a trivial connection, we have a bunch of vector bundles stacked up like this, then what I can do is I can start at this point, go over here, have this vector sort of transform some amount, but then I can just like come back, okay? And then what'll happen is like this transforms, this transforms, this transforms. And because all of the vector spaces are identified with r to the k, what's essentially happening is like all of these things are identity transformations. So when you go to some place and you come back, you're gonna end up at the same vector that you started with. So if you remember, my initial description of parallel transport was like, if you move along some direction, you're like looking at how much does your thing change by infinitesimally. And that's sort of what we've accomplished now that we've talked formally about connections. In these local trivializations with connection matrices, is that if you move some amount, that little derivative term is telling you how much to rotate your vector space, and you get to this endpoint. If you try to come back the same path, then it's going to undo all those transformations and end up back where you started. But what could happen is you could go down a different path, and you end up with something else at your endpoint. So what you can do is you can, so there's, I guess, two perspectives you can take from this. You can look at P and look at two paths, gamma 1 and gamma 2, and you can look at what happens to parallel transport as you transport some vector over here along gamma 1 to some vector over here, and along gamma 2 to some other vector over here. And if your connection is trivial, comparing one vector over here to where it ends up is like a completely basis independent statement, right? It doesn't really depend on what you're saying. You're saying, this points in that direction, does it point in the same direction or not? So if your connection was trivial, these two would have to be the same thing, regardless of how you present your connection, regardless of how you solve. By the way, the parallel transport you can sort of see as a solution to the ODE that the second derivative of your vector field with respect to the direction that you're moving, plus your connection times this equal to 0. I think that's the formula. And this has a nice interpretation. This is basically how GR works, that this connection term comes from the metric that you put on. It comes from the rigidity connection, which we'll hopefully talk about later. And this is essentially like, if this was 0, right? Then it's just saying that the acceleration is 0. What this does is it sort of says, if you have the presence of a metric or a presence of a connection, it's going to like sort of move your particles. It's going to essentially put a force on your particles. So this, you can sort of think of it as, this is like MA, and this connection matrix that you have in local trivialization is like the force. And actually, interestingly, if you formulate electromagnetism this way, you can actually also see electromagnetism as a similar sort of equation. But yeah, so if the solutions to these equations are going to be the parallel transport guys that you have. Maybe should be just not second derivative, first derivative. Yeah, if you look at the geodesic equation, then you're going to get something that knows, of course. But this is just saying that the covariant derivative of these is zero. Yeah, so it should look like this. In the direction of this. So this is no matter how you solve this first order ODE, the endpoints is going to be like comparing whether or not they're equal is independent of the way that you set up your problem. So this gives us a test as to whether or not our thing is true. And for sort of ease of working with things, because this involves a linear map from EP to EQ, and you need two linear maps here. Instead, what you can do is you can sort of follow this loop around the whole way back, and you can see whether or not your vector ended up back where it started. And so this gives you a linear map, EP to EP, and if this is not the identity, then you have some evidence that your connection is not trivial. Do you have a question? Okay. Does this make sense? Goal? Okay, so since I only have 5 minutes, I won't go into the details of curvature just yet. Instead, what I'll do is I will give you some examples, or an example, I should say. Let's draw a big sphere. Okay, so this is the Earth, and this is you on the North Pole. And you say, no, I want to visit the equator. So you start moving in this direction. And you get to the equator, and you're looking down, right? And then you're like, I don't know, is Mexico on the equator? You're in Mexico. And you're like, I want to like go across to like Egypt or something, right? So then you start moving sideways, but because you're intensely concentrated on looking in the same direction, you just walk like this. And so you're always looking down. And what I mean by this is like, this is the vector being parallel transported across, right? So you're always looking down. You get to this point, and you're like, I kind of miss the North Pole, so you head back. So go back to the North Pole. What you'll find is that you aren't looking at the same way that you started. And this is this is the notion of holonomy. Holonomy is the notion that you go from a starting point along some path and end up back where you started, and the amount that your vector changes by is what's called the holonomy transformation at that point along the path. So a non-trivial holonomy gives evidence to non-trivial connections. And what we'll see is that the curvature is essentially an infinitesimal holonomy. And so if the curvature is non-trivial, that tells you that you have a non-trivial holonomy. And the curvature actually transforms in a very nice way. It transforms in that sort of conjugation way, where if it is zero in one frame, then it's zero in all frames. So if you compute the connection, then that'll actually give you a test as to whether or not your connection is at least locally trivial.
Do you know if there's a connection between holonomy and vary phases?
Don't know what vary phases are, we can talk after.
Okay.
Yeah, it's almost certainly something to do with parallel transfer. So one thing that you can say is like, okay, what if, so there's a special type of connection. It's called a metric connection. So on your vector bundle, you can put a metric. That's another way of rigidifying your vector bundle, where it says, I'm going to specify a size of each vector space. And putting a metric on your manifold, essentially the same as putting a metric on the tangent bundle. And so you can look for connections which preserve the metric, which is to say, after I parallel transport, if this vector was this length, I don't want to stretch or shrink it as I move along. I'm going to keep it the same length as I move along. So those are called metric connections. And so it turns out that the rigidity connection, which is what is going on here, is a metric connection. So it won't change the length of your vector. So if you have a linear transformation in R2, which doesn't change the length of vectors, what's the only possible thing that can happen?
So your rotation.
It's rotation by some amount, right? So what amount do you rotate by? So I claim that this is a really interesting theorem on a sphere. On a sphere, the amount that you rotate by is the following. Take these angles, alpha, beta, gamma, and what happens is if we draw if we go outside the sphere into 3 dimensions, and we draw the triangle connecting these vertices, then we know that some of the interior angles of this triangle are 180. Right? But if we push out a little bit, then what will happen is like each vertex is gonna expand a little bit. So the angle sum of alpha plus beta plus gamma is gonna be slightly more than pi. So what we can consider is the number alpha plus beta plus gamma minus pi, right? And so this is called the angle excess. And I claim that the amount that you've rotated at the beginning is going to be exactly the angle excess that you have at your vertices. So how can you see this? Well, let me ask you a question. What's the interior angle sum of a polygon with n sides?
N minus 2 times 180.
Yeah, right? So it's pi times n minus 2. So when I was thinking about why the holonomy should be related to the angle excess, I realized that there's actually a much simpler statement that you can make, which is that if you have a polygon, instead of considering the interior angles, you consider the exterior angles, which are these angles. Right? And let's see here. Yeah, so this formula tells you that at every point, if you take the sum of the interior and exterior angles, then you're going to get a copy of pi at every point, right? So if we look at what the sum of the exterior angles is, that's going to be pi times n minus this, which is equal to 2 pi. But there's a much easier way to see that the exterior angle sum is equal to 2 pi. Put this on a line, right? And just like rotate the polygon until you get back to starting position. And then the amount that you rotate until you get to the next edge is the exterior angle at that edge. And you rotate a total of 2 pi. So you have this very simple way of seeing that the exterior angle sum is 2 pi. So how does that relate to this? Well, what you can do is when you get to the end, if you're comparing the angle, so let's say that you're walking this direction, right? And then you get to here, and then you continue walking along this line, but you keep facing the same direction. Okay? If you compare the angle that you're looking with the angle that you were walking in, at each corner, that changes by the exterior angle, right? So this says that as you go to the next one, if you keep looking in the same direction, comparing your direction with the direction that you're moving in, it's going to change by the exterior angle. And the same thing holds over here, right? And so what happens is, in this case, the angle sum is 2 pi and you end up back where you started, right? If you move around this way, you end up back where you started. But in this case, you're getting shifted a little bit more because the angle excess here is a little bit more than pi. So another way to write this is, let's see here. So if you look at the exterior angles, then that's looking at pi minus alpha plus pi minus beta plus pi minus gamma. And you can look at how much this exceeds 2 pi. And so what you see is that this is exactly equal to negative of this quantity. So looking at this exterior angle is the same as looking at the angle excess. And so we see that the exterior angle measures the holonomy because it measures how much your direction changes with respect to the direction you're moving at each point. You accumulate the exterior angle at each point for that. And, I mean, you know, orientation doesn't really matter, you can just redefine what you mean by rotation. But this tells you that the amount that you rotate at the end is the excess of the sum of the exterior angles from 2 pi, which is exactly also the interior angle excess from pi. So that's a pretty cool little way of seeing this. But yeah, so in general, the theorem is going to be that the holonomy, if you look at a surface and you have a metric connection, the holonomy around a loop is going to be actually the total amount of curvature contained inside that loop. So if you have like a very small triangle, the angle excess is going to be very small, and the holonomy is also going to be small. And you can expect the holonomy is small because you haven't moved very much, right? Like things locally look pretty flat, so you expect that if you like go like this, I'm not going to change my direction. But it turns out that the amount that you do change your direction actually depends on what the curvature space is, and that's sort of actually like a definition of the curvatures. Yeah, that's all for today. Any questions on anything? Next time we'll talk about curvature. Probably try talking about metrics, Levi-Civita connection, and Riemannian curvature. And if we have time, talk a little bit about complex vector bundles and Chern crossing.